Hello. Today I will prepare for you some the three following tasks about weighted graph, about find a way in weighted graphs. And today we consider some problems on matching and vectors cover topics. Before we started, I think we should repeat what we do, what I tell you in previous lecture, because in the middle of the lecture there's a sound was missing, and okay, matching in graph is a set of edges where no two edges have a common vertices, and we considered the alteration operation that allows us to increase matching. Then we consider what is augmenting pass, alternating pass, and consider Birch's theorem that helps us to find maximum matching. Then I provide you algorithm based on the theorem. Where is it? Here it is. We just want to increase our augmenting, increase our matching until there is no augmenting pass, and we consider Kuhn algorithm that works for only bipartite graphs. So here's algorithm that works only bipartite graph. This algorithm finds augmenting pass and performs alteration operation. It works based on DFS. We just in DFS we consider what we do when we enter in our function DFS, and what we do when we exit from recursion. So we check here we check just we this just here we check that this vertex, this current vertex is considered before or not. If it's considered, we return, and on exit we just apply when we find augmenting pass. we just apply iteration and get iteration, get that if we launch this function, if we launch this function by all the vertices, in each iteration we increases our matching by increment our matching or don't increment, and get that and get maximum matching. But we didn't prove that if we do matching in such way, if we launch this function in such way, we get maximum matching. I prove it later, a little bit later. Then we consider it what is independent set, what is vertex cover. I told you that if we can find independent set, we can find click tool. We just take addition. We just take addition, graph with addition. What is addition? It's universe mean minus edges. Universum. What is universum? Universum is vxv minus this set. We don't want to have loops. We take this graph and if we find independent set in this graph, in our graph G, we find click. We find click if we find all the independent sets. We get that, find all the clicks. Okay, and then we consider algorithms that allows точнее Kuhn theorem that allows us to find independent set in graph, in bipartite graph. We can do it for ON complexity. By the way, if some graph, we can do it for if we can find independent set, we can find clicks too. So in bipartite graph, we get that we can find clicks for ON, and in general we can find clicks for this complexity. So this algorithm is very useful if we have bipartite graph. I prove it a little bit later, and I prove it a little bit later this theorem too. But before this, we consider some tasks on lead code. Okay. So consider this task. So we consider this task. Так, who's there? Pin and Masube read this task. If you have ideas how to solve it, write to the chat. What is bipartite graph? Once again, I defined it like this. We have two sets. We have divide our graphs. If we can divide our graph into two sets, and in this set there is no this edges, the graph is bipartite. And pay attention for this node. So, how to solve it? This task. We need to just define this graph is bipartite or not. Do you have ideas? No, we can use this equivalent definitions that graph is bipartite. What will be most useful for us? Here G, its number is a number that we can call a paint vertex of our graph. So two vertices. There's no two vertices in our graphs that have the same color. It's minimum count of colors that we need. It's clear that we in this task we just apply this criteria or this criteria. The graph is bipartite. But what is the most easy way to check that graph is bipartite? Use these conditions. You can say I think I can understand you now. Okay, we can apply this criteria to find to define this graph is bipartite or not. We just color what we will do. We just paint our vertices. How we can paint our vertices in which order. We can do it in any order, in BFS and DFS. We just color the first vertices, the first vertex that we consider as red or blue, or orange or blue, or what you will like, and all the vertices are white. It means we doesn't visit these vertices, and we just launch DFS and paint next vertices alternately red or blue. And if we can paint our graph in these vertices, we get that our graph is bipartite. For this example, we paint this vertex red, this blue, this is blue, this as red, and this is blue, and we get that we have two vertices with same color. In this way, we paint them without any problems. So how to define in algorithm in DFS that we paint two vertices in the same color? Okay, we paint, if we consider our DFS, we just check on when we enter to our DFS, uses if we paint in the same color or not. We can read comments. I think it is easy to understand what we will do. Once again, we consider what we do in DFS when we input enter to our vertex, and what we do when we go out from this vertex. In this way we consider graph. We consider graph, color, check in when we enter to our current vertex, we check that previous vertex wasn't the same color that we want to paint it. If we it can be painted like in blue or white, and we check that it doesn't red. It is not red. So after we find all those paths, we consider current vertex, and we consider that we find some paths that we can paint like red and blue. So we check this for every path, and if some path we can paint like red and blue, we just return and return false. We perform it for every vertex because we can get that our graph is have component, and that's all. Second task. Second task. We want to split a group of n people into two groups of any size. Each person may dislike some other people, and they should not go into the same shop. So we need to check. We can do such. We can split everyone into two groups or not. What we can do? I missed you. So we can do it in the same way. We just do the same thing. Paint our graph with red and blue and check that we can do it or not. We just divide our people in L group, in L group and R group. Okay. I think we consider another two algorithms. I don't know why is it hard. It's так. Means two cameras on the three nodes, where each camera node it can monitor its parent itself and immediately in its immediate children. We given or only binary tree. That what what is the problem to check? Okay, we just begins from root. We just begins from root. Paint painting like in blue and so on, red and blue, and count of red vertices will be count of cameras that we need. That's a very easy task. I think we if we consider any graph, we can use algorithm that finds vertex cover. It will be any bipartite graph, not any graph, and we can consider this algorithm that find vertex cover, this Kuhn theorem, and get our vertex cover, our mean vertex cover. But this task is too easy, I think. Okay, if there's no people, there are no people, we can prove this theorem. We can prove this. Where is it? Kuhn algorithm. We can prove this. How? That this works for if we launch our augment alternation function, that we get maximum click, maximum matching. Okay, I think we can continue in this. Так, we can continue this. So we need to prove that this order is true, is correct. So it means so why is y is after iteration through where there is no augmenting pass. Passes. We can consider statement. Let m prime matching some matching that we give given from m some matching using iteration operation. Iteration, but on with some augmenting pass. We need to find this pass. To do iteration. Let from where there is no exist augmented pass. In M, and that means from where there is no augmenting pass to. If we prove the theorem, statement, we prove that if we consider this order, we consider always unmatched vertices, and that means we on matched vertices we there is no if we if we return from some vertices, some vertex, and try to do iteration, we get that we don't if we can't increase this anymore, this set, this matching anymore. We can't do it in if we return in any vertex that we consider. Okay. So that we consider it. So okay, m prime matching given from m using iteration. So we consider this m strich m prime given using iteration. Means augmenting pass look like this for m. So we can consider some cases and get contradictions, whereas we consider counterfactual proof. Okay. What will be the cases? Так. Блин. Ладно. So we consider counterfactual proofs. We consider that there's some augmented path in M. So this path can be intersect with our M prime or not. We consider that this path doesn't intersect with our M prime. So we get that this path will be augmenting path for M2 because we can consider just extract edges from. We consider some path. We just extract edges and get augment path for M. So for where we get augmented path in M. That means we get contradiction. Second case, it's convenient to draw in this. We get that we consider some path, and this path is intersect with our matching M prime. Forget that what this last edge will be in M or not in M. So if it's in M, we get that we get vertices that have common edges. So this doesn't exist. That means this edge doesn't belongs to M. If this edge doesn't belong to M, we get that we can continue augment path with like this, like this, or this, if this edge doesn't belongs to M. This edge doesn't belongs to M and doesn't belongs to M prime 2. And get that we can continue if we find this this path. We get that one second. This just 1 second. From where there's augmented pass. Okay. In M. In M prime. This case is not possible too, because such we can consider that the edge doesn't belongs to M and doesn't belongs to M prime. Get a contradiction. I find mistake. Okay, and because it's augmented for M prime, so this is the last case when we consider somewhere that belongs to edge. It means we get augmenting pass. It means what? It means what? It means that Y matched in relation to M, and we don't we can consider this case. So that's all. Those all the cases when it intersect in some middle, when it intersect on ends, and when it doesn't intersect and it is not intersect at all. So that's all. It means we can just apply this order and consider this theorem, Kuhn theorem. In bipartite graph there is of mean vertex cover equals to size of max matching. We consider algorithm. We prove this by конструктивно. Я не знаю как. I don't know what English word for this. We direct edges in this graph, bipartite graph, from R to L. There's we consider unordered, undirected graph, undirected bipartite graph, and we just direct edges in such way. So then we launch the FS from all unmatched vertices of left side, and we get these sets. These sets L minus and R minus means that we didn't visit at all these vertices when we launch from unmatched vertices. No, for example, this means that in this set there's in this set we get only matched vertices. We consider only matched vertices. So then we get that L plus R minus plus union R minus. That means mean vertex cover. Why am I overwrought like this? It's not true. This is independent set, max independent set. and else will be mean vertex cover. And by the way, we так, in this algorithm we must to find matching before this. So we find matching, maximum matching using Kuhn algorithm. Because graph is a bipartite. Then we direct edge, then we launch the fs, and we just get this. Just four. So we consider four sets: L plus, R minus, L plus, R plus. So this sets doesn't intersect, are not intersect, and give us our graph, bipartite graph. So notice obvious facts, some obvious facts, which we just want to consider edges and to get independent set, for example. Which edges are definitely missing. In this graph. Notice that if we consider this edge, that means this edge doesn't exist because this kind of edge doesn't exist because what? Because if we launch the fs for L plus, that if we launch the fs, we just we get that in L plus we get much vertices, and we visit these vertices. That means that these vertices can be belongs to R minus, because we visit this vertices. Next case, R minus, L plus. By the true, because if we consider R minus, we get that this edge belongs to matching, and if it means this vertex, it means this vertex belongs to match 2, and we get that get that we launch for our DFS for some unmatched vertices that belongs to L plus. Get that we just walk for our graph and get into this vertex, and that means then we go through this edge, and this means that this vertex doesn't belong to R minus because we visit it. So and what kind of edges R plus to L minus? Because if we visit R plus, we get that we visit L minus 2. L minus 2 vertex from L minus 2, and this vertex is not L minus. So this this gives us independent set that L plus R minus is independent set. It means L minus union R plus vertex cover, because addition to independent set is vertex cover, and we want to prove that this then we want to prove that this set is maximum. Then we proved that this set is minimum automatically. So we consider vertex cover, not we prove that this set is minimum. So we consider it in notice that in this set R plus union L minus there are no matched vertices. I already say why. L minus, it's obvious, and R plus once again, if R plus we get unmatched vertices, that means in our graph G, Okay. If we consider unmatched vertices, unmatched vertex in R plus, we get that there is augmenting path in our graph, and this and using this theorem, where is it? Okay, well, this theorem, we get that M is not matching, and that is contradiction. We consider R plus, and if n plus there is augmented path, there's unmatched vertices. Using DFS, we can find augmenting path because we visit this the last vertex and get that. Then in G there is augmenting path. There is augmenting path. That's not true. Okay. Так. And consider now this set L plus to R plus and L minus, and we want to prove that this set is maximum. L minus L plus minimum vertex cover. Okay, we prove that it's vertex cover, and we want to prove that it's minimum. Так. Okay. We consider estimates. We need to prove that this set less or equal than matching. Why is that true? If we consider our R plus, L minus, and R plus, we notice that every edge, every vertex in this, if we consider vertices, we notice that there is not exist this edge or this edge or this edge or this edge. Why is it true? Because we just considered it. L plus to R minus doesn't exist. R minus, L plus to R minus doesn't exist, and R minus to N plus doesn't exist. And we get that. And 1 second. L minus to R plus exists. No. We just consider. We interested in only this edge, this kind of edges that from R, that located from R to R to L That means it belongs to match to our matching. We just defined it like this, where what here we consider only these vertices and only these edges, and we get that this edge doesn't exist at all, R plus to L minus, and this edge doesn't exist at all to R minus to L plus. That means we get only like these edges or these edges. And notice that if we consider matching with every matching, every each vertex have unique edge. If we consider some vertices that belongs to L or R, we get that any edge and any vertex have unique edge. Each vertex have unique edge, and get that vertex has unique edge. And get that this estimate. But we didn't. But we want to prove that L unique union to R plus is equals to M. Why is it true? We consider L minus R plus union R plus less than M. Why is it true? Sure. Why is it true? Because if you have matching, just 1 second. I don't remember why is it true. Let me так. Sorry. If we consider some, we consider vertex cover as we consider a vertex cover, we consider some vertex cover and maximum matching, and it's easy to understand that maximum matching will be at least contain matching. Ну, как бы, if we consider some matching, we get that we want to include all vertices of some edge, because if we don't do this, we get that some vertex in our matching, some edge in our matching, our graph doesn't consider it at all. Okay, and we get that this case is not true, and we get that L plus L minus union R plus equals to M. And we get that we can't take less than this count, and this will be minimum vertex cover of our graph. Okay, and this means this set will be maximum. So that's all about matching. We have some means. We can I think solve some LeetCode task, and notice that complexity of this will be O(n), because we just consider the fs. We just consider the fs in our graph, and as graph is bipartite, we not only n plus m, v plus e, v plus e. V plus e. So we get that we find maximum matching using DFS. That's O(n). Direct edges, that's O(n). Launch DFS, that's O(n)(2). If notice that we launch DFS only less than twice, and for any vertex, if we visit it, or if we unvisit it, or if we visit it. Okay, and we just get this and this, and we get that we find a way how to get independent set, maximum dependent set for O(n). It's very fast because we consider it. I already say that we get O(n), O2 to the power of n divided by 2 in any graph if we want to find independent set equivalent to maximum independent set. It's task maximum independent set equivalent to task find maximum click, because we just take this and get that we want. Okay, we consider how to find maximum independent set, minimum vertex cover, and that's all about graphs. I think we consider in the next lecture how to find деревья отрезков. I forgot about how to in English. Segment tree. We consider segment tree. It's graph 2. Ну, ладно, it's graph 2. So, we consider this in this task. But consider this. I have already told how to solve it. Okay, consider this minimum of vertices to reach all nodes. given a directed acyclic graph with n vertices, find the smallest set of vertices from which all nodes in the graph are reachable. It's guaranteed that a unique solution exists. Ну, you want to find maximum matching or minimum vertex cover in this task. By the way, так, given directed acyclic graph. Directed acyclic graph, it's a forest. It's no. Okay, we just what to do? what to do? We just apply this idea how I told in this task, and apply on every component, I think. But why is it medium? This and previous task is hard. I don't have any idea why is it medium and previous task is hard. It's very unusual. Okay, do you have ideas how to solve it? I have one idea how to solve it. We can pass through this graph in topological order. In topological order. We just pass this graph. We can just consider topological order of this graph. Because it's directed and acyclic. We get topological order. Topological order. Some topological order. And just paint first vertex as blue and second and launch the fs for any vertex, and any vertex is white, we paint first as blue, and we just what to do? We just paint next vertices as we did in first lead code task as red. Paint this as red. This is red. And next, we consider BFS order, and next edges and next vertices will be will be blue. Will be blue. Will be blue. And we and count of and the count of blue vertices will be answer. What will the answer? Так, okay. Do you understand the idea? Why is it true? Or what? Do you have questions? Okay, you don't. And we get that. Not to. Once again, not so free. Okay, we get. And and not 3. This this okay, this is not just 1 second. No, once again, I thought you in this task you need to find vertex cover, minimum vertex cover, but in this task we find просто just some. I just use the FS and just how to do it. No, we can use topological order, just topological order, and print the first vertex in topological order. Сейчас that we didn't reach. And that's all. And we count these vertices that we don't reach in topological order when we launch the FS. We launch the FS from null. For example, we get 1 and 2. Then we try to launch the FS, but we visited it. And then we launch the FS for 3. That because topological order of 3 is less than topological order of the sets of this. It's task about topological order. No, I think you get idea how to solve it if you want to find minimum vertex cover. In bipartite graph, in this algorithm, we consider unoriented graph, just an analytic graph with cycles, an unoriented bipartite graph with maybe cycles. Нет. Сейчас. 1 second. Second. No, it's maybe cycles. Okay, this algorithm is easier than this. Okay, last task. House robber. No, let I show you Okay, what? No. Where? No, topological order, what sort? No, then. Okay, just topological order, how I told you. And in this task, okay, we want to maximize our we didn't consider vertex cover because we can get minimum vertex cover because we can get that Robber that oi. Because we, for example, can get this 1 1 6 and we just mark this vertices, but this not vertex cover. Okay, what the idea will be? We can use the pair or what? What we can use? Ух ты! I never seen this before. Medium. Okay, the pair in this situation doesn't easy. It's not easy. Do you have ideas how to solve it? I have not. Пока что. Так. Ну, так, ну, what we can do? We can use some kind of the pair. We can consider of course we can use some kind of the pair. We can consider only two last vertices, only 3 last vertices, and choose every time we choose maximum of these 3 vertices. we every time we choose, we use not greedy algorithm, we use not DP algorithm, we use greedy algorithm. And every time when we add vertices, add some vertex, it means we consider it. Just consider it. We check what. But we can use the pair. We can use the pair. It's just like an. It was in just like an этот grasshopper. But. Sure. It was just like in grasshopper. It can be implemented just like in grasshopper. Or not. Sure. If we consider some graph that we already know, in which we already know dp g, we have dp, and we want to find dp e, dp of some e. dp can be unordered map, I think. Ordered map. Okay, it can be just сейчас. It can be just an ordered map, and we consider last two. Нет, that's bad. That is bad. It's not. Okay, E is dp e. What will be dp e? The first size, нет, answer, maximum cost of the first e vertices. Consider it in the FS. Consider it in the FS. And we just want to consider the P. Так, ну тут нет, it's an ordered map. It's an ordered map, not the first vertices. The first vertices considered the FS. No, it's not vertices. Сейчас. Как бы так? И vertex. TPV. Max cost of the first what? The first vertices of considered in the FS that the first E vertices considered in the FS that ends in and in V. And how to calculate the PV? The PV equals to the P V. Так, the PV, как это написать? The PGV. ЖВ. The PGV максимум. The PGV. Just 1 second. Maximum the PGV. Greedy will. It's easier. I think the PGV plus the PGV plus the P. No. The PGV. The P. G. V. Sum. Not sum. Maximum. Maximum. Maximum V. Нет, V, not V. Maximum of the set. I think that's true, but this is too hard to implement. I think greedy algorithm would be better if we just consider first the vertices and consider other vertices, and if t plus y сейчас if total cost g if total cost plus t 4 vertices. That's a bad. That's very bad. Yeah, no, it's not bad. The total cost plus, not total cost. Just if x. This will be in several cases. X plus c less than y. We just consider that in this case. Okay. Так. No, we consider 3 vertices, and this case will be if what? It t parent t is red or what? We consider this if and else. We just no, x plus c, x, we add x and t to our answer, else y. Another case, else. Блин, ну как else, we consider we want to take y or x or x. X to answer. Or y to answer. A lot of cases. Okay, I think it's time to consider solutions. Batch step tracking, dynamic programming. Let's consider dynamic programming. Oh, okay, another map. Так. Root left, root right. TP root left, TP root right. I thought this. We consider only binary trees, so we can consider it like this. And what am I doing? Am I consider it that? Consider it this. No, this will be the same, I think. Okay, I'm very happy that my solution works. Greedy algorithm works too, but it's greedy. Where is greedy? In C++. Oh, okay. I see. No, unfortunately, I considered some graph. I considered some graph, but the solution works too. Or not. It's not works. Because we have this case. If we consider already this graph, then we consider this edge. We get that we consider this solution is not works, but the idea is correct, because in any graph it's hard. It's hard. I think it's any graph we can use segment tree, and when our graph is just binary tree, we can use this. Okay, that's all. I think that's all. Надо было. I should consider solutions or before. Ладно. Okay, that's all. I think that's all. I post 3 tasks on Dijkstra, on path algorithms, on sources path algorithms, and that's all. See you later.